Hey, welcome everyone to our Institute for Quantum Studies seminar this week. We're very pleased to have Aephraim Steinberg visiting us from the University of Toronto. Thank you for everyone for coming in, even though it's spring break. So it's great to have everyone here. I just want to give a little introduction to Aephraim. So he did his Bachelor's of Science at Yale University, and then did his studies at École Normale Supérieure in Paris. His PhD is from the University of California, Berkeley, where he got started on many of the topics he's interested in to this day. And then he did postdocs at the University of Paris, at NIST, and then was an assistant professor at the University of Toronto. And he spent most of his career at Toronto with various visiting professorships in Vienna and other assorted places. He's won numerous awards throughout his career, the Herzog Medal, a fellow of the Optical Society, the American Physical Society, the Institute of Physics. What else has he won? He's won all kinds of things. The Rutherford Medal, the McLean Fellow, the Senior Fellow from Safar. Okay, so lots and lots of awards. We know him for many years as being someone that's interested in really a master in quantum optics, but also very interested in foundational questions in quantum physics. Not only optical physics, but also in atomic physics as well. And we've had the pleasure to be able to work together on and off with many other, also other people in the room over the years. And hopefully we'll have a soon awarded Templeton Foundation grant to do more work together. So today, Aephraim is going to give us a sort of a broad scope talk entitled Everything You Always Wanted to Know about quantum tunneling, photon propagation, and quantum robots, but never thought to ask. We're very happy to have you.
Thank you so much for having me down here again. It's always a pleasure to come back and get to talk to you folks and learn new things and think about some new ideas. And indeed, I'm going to try to overwhelm you with everything you always wanted to know. And as I said, interruptions are always welcome, and I'm happy to run out of time before the end and tell those of you who are interested about the stuff I didn't quite get up to. In the background there, you may not see it very well, but it's two of my old students, Chris Eleanor and Mirko Zirka, demonstrating the truly Canadian approach to laser cooling, which is a bucket of snow being poured on an apparatus that was misbehaving in those days. Something of a delay. That's a somewhat more recent picture of the group and some of our alumni. We work, as Sandra mentioned, on experimental quantum information and foundations, but we prefer to think about it as just fun with atoms and photons. And I want to give you just something of an overview of our group and our research interests today. And then I'll try to focus on three particular topics we've been working on lately. So our interests span at the experimental level, ultra-cold atoms and entangled photons, along with an attempt to merge those two and study the quantum level of light matter interfaces, but overall seeking to address fundamental questions in quantum mechanics. So on the atomic side, there are a number of different things that we're looking at. One of the things that Andrew alluded to that's obsessed me since my graduate work is tunneling. So I'll talk a little bit about that today. That uses a Bose-Einstein condensation apparatus. We're currently building a second such apparatus with new capabilities in collaboration with one of my Toronto colleagues. And we have another experiment that's moved through a bunch of different iterations, looking at things ranging from quantum error correction to resonances in quantum kick rotors, but these days is used to study the quantum interactions of light and matter, and in particular, this rather weird question we stumbled along, which is how long do photons spend, quote unquote, in atoms while they travel? On the photon side, we're interested in trying to figure out some semi-practical questions, such as whether you can make photons interact with each other, what happens across the beams, but also how you can use optics to do the most precise measurements, squeeze on light, as we used to say, or this is what I think of as my quantum optometrist device, but that's actually something we used in collaboration with Nicole Younger-Halpern and David Arvidsson-Shakur to study the role of non-classicality in metrological advantage. Nicole over there with my student Noah up in the upper left. More recently, we're looking at questions about what quantum agents are and what imaginary probabilities and things like that are, sort of just in manner we were just discussing a few minutes ago. But to back up a little more, I don't know how many of you are fans of the Black Mirror TV show. This was my favorite episode so far. This is a quantum computer, right? We barely know how it works. Some of you will take issue with that. And, when I talk to my students, it's not true. We do know how they work. But actually, that's a lie. We know how they work, but we don't know why they work, right? There are fundamental questions about the power of quantum computing that we do not know the answer to. I think it's really important to remember that. So let's kill this quamputa, in the words of Salma Hayek. But the serious reminder behind that is that it took 30 years from the EPR paradox and Schrodinger's original enunciation of the ideas of entanglement before we had Bell's inequalities that we think of as this landmark. And it was another 30 years from that before the ideas and applications of quantum computing that got the world to sit up and notice, which were Shor's algorithm, quantum error correction, and some related things. And it's been another 30 years to the point now where we have companies claiming that they're making real large-scale quantum computers, but we're still not solving, frankly, real-world problems on those. All throughout those decades, there were people asking really deep questions about things that the mainstream community thought were already resolved. And for a lot of that time, it was unfashionable or even dangerous to one's career to be focusing on these questions. And it's wonderful that folks have now recognized that those were important questions and they led us to these new capabilities. But it would be wrong to conclude that we're done. That the guys who took risks 50 years ago, thank heavens for them, we're going to use their results. And now we're just going to sit here and talk about the engineering. There are still deep questions out there. Physics has not changed that much. And we need to keep asking those questions. And I keep telling all of the quantum computing, funders and organizations not to forget that. One of them said, oh, no, we have no intention of killing the goose that laid the golden eggs. And I was trying to say, we're not asking you to stop killing us. We're asking you to feed us better. I'm hoping that they get that message. So what I want to do is talk about 3 different topics that we're focusing on these days in the lab and some of the questions that they raise for our future research. I'll give a little bit of background about what I call quantum archaeology, but that's somewhat bringing coals to Newcastle in this environment. I'll go through it quickly, but I think you all know what I'm alluding to. And I'll talk a little bit about my most longstanding project, asking in quantum tunneling how long particles spend in a region they're not allowed to be in, and our more recent work and future experiments, hopefully, on what happens when you see a particle in a region that it's not supposed to be. What does that do to the particle? Somewhat more recent experiments on the photon propagation, where really what we're asking is, why does light slow down when it goes through matter at all? How should I think of what the light is doing as it goes through a piece of glass or a cloud of atoms or something else? And then the weirdest stuff we started working on recently through an F2XI Templeton grant is this question of what it would mean for something to be a quantum agent, right? You and I are agents. We observe systems, we make decisions, we control systems, we do our experiments or whatever it is that we do. And normally we think of that processing as classical processing, even though there are folks out there asking, do we know that? Is the brain, in fact, a quantum mechanical processor? We don't know the answer to that question. Nevertheless, you could imagine building a control computer that's running an experiment, because in reality, it's computers that run our experiments nowadays, and have that, maybe not today, but maybe in 10 or 20 years, be a quantum computer. And ask, what could that quantum computer do when it's controlling an experiment that's maybe very different to what a classical graduate student or a classical computer does running an experiment? What is that quantum brain experience? And what are its effects on the environment? So quantum archaeology, what I really mean by that is the bigger question. Is the wave function the whole story? If the wave function is the whole story, then I can't tell you, which part of the wave function a given particle is in or something like that. It becomes meaningless. But I'd like to know if I could learn something else when I make future observations. And the picture that I have in mind is this distinction between our familiar conventional wisdom about quantum mechanics, which is that you're not even allowed to ask about things you didn't bother to measure. I send a photon through an interferometer, it lands somewhere on a screen, and if you start asking me which slit it goes through, then Jeff Kimball or somebody gets out his gun. You're not allowed to ask those questions. But of course, if you think about classical physics or archaeology, we dig up bones, and from those bones, we conclude what was walking here 65 million years ago. We look at the cosmic microwave background, and we try to draw conclusions about what the universe was doing 15 billion years ago. And normally people say that's a distinction between classical and quantum physics, but they're wrong, because as far as we know, there is no classical world. The Tyrannosaurus was quantum mechanical, the cosmic microwave background was certainly quantum mechanical. So when we do this, we are drawing conclusions about the past of quantum systems. So we know that we can do that. The question is, what are the limitations? The same way the uncertainty principle places restrictions on how much we can say about the future, it places restrictions on how much we can conclude about the past. But we do learn about systems, both from how we've prepared them and from where we find them later on. So my favorite example of this from Yakia and his collaborators is this 3-box problem, where you all know I could hide, I don't know, I think it was a $1 bill in my childhood, but it looks like they're $20 bills now. And I could hide some money under one of 3 bins and ask you to find it. And the quantum mechanical extension of this is to say, I don't even need to put the bill under one of the bins. I could hide it in a superposition of box A and box B and tell you that's where it is. And I'm a fair-minded guy, so I don't then ask you to find the bill because we both know you'd only have a 50% chance. I offer you additional information. I say, suppose I tell you that I prepared it in A plus B, but I promise you that I'm going to find it in B plus C. Now, of course, I can't promise you that. What I can do is say, if I don't find it in B plus C, we'll start over. We're not going to count that trial. And the question is, what can you say about what the bill was in between? This is the wrong audience for me to let you try to answer that question, so I won't, but I'll just tell you the sociology of it, which is that almost invariably, when I ask this question of physicists, there's silence in the room. And eventually someone will raise their hand and explain why you're not allowed to ask it. They'll tell me it was 50% in A and 50% in B until you made the measurement, and then your measurement disturbed everything, and then it changed. And now it's in B plus C. I ask the same question at public lectures, and there are always a few people in the audience who raise their hand and just give me the right answer without any hesitation. The right answer, of course, is B. And the classical reasoning is simple. The classical reasoning is I don't know what 2 means, and I don't know what plus means. But I think he's saying he put it in either A or B, and he found it in either B or C, and the only overlap is B. And it turns out that classical reasoning is correct in the measurable sense given by Yakiel's weak measurements. It also turns out that if you draw the picture the way I would experimentally, it becomes obvious again to physicists. You ask, what would it mean to do this experiment? How do you prepare a particle in a superposition of 2 boxes? Can anyone tell me? They put a photon in a superposition of 2 places.
Use a beam splitter.
Use a beam splitter. So this is what that experiment means. I take a photon, I use a beam splitter, I put it in a superposition of box A and B. There's nothing in box C yet. And then I look for the photon in a superposition of box B and C, which just means I combine them on a beam splitter. Now, what I'm now asking is, if I sent a photon in here and found it here, what can I say about where it was? No one I know would look at this diagram and have any hesitation about that. It obviously followed this path. It's the only one that connects the input and the output. And you draw that picture and people say, oh, of course, but before you draw that picture, there's, oh, you're not allowed to ask. That's not what a measurement is. That's not fair. Of course it is. Of course that's fair. And it means operationally that if you put some probe around boxes A, B, and C, that probe would be unaffected by the photons that landed here. This probe would be unaffected by the ones that landed here. But this one would see 100% of it. Now that might seem trivial, but of course what's interesting is I could do something more complicated. And why shouldn't I still ask for some arbitrary interferometer and arbitrary phase shifts? How much for a given post-selection affected each of these probes? I should be able to ask about that. And that's what I mean by quantum archaeology. Let's say we have systems where we have an initial condition, but we also make later observations. Let us learn how much we can say about the intermediate state of the systems. So the thing that first got me into this was this long-standing tunneling problem. I guess what I should say is the thing that first got me into it was Yakiel giving a series of lectures when I was a grad student, none of which I understood. And a few years later, by realizing that they probably contained the answer to what I'd been worrying about anyway, which is this problem. I think everyone who's taken quantum mechanics knows, or at least has known at some point, how to calculate the probability that a particle will show up on the far side of the barrier. And most people never even stop to ask, how long does it take before it gets there, before it gets through this forbidden region to the other side? Certainly, no quantum mechanics textbook I've seen, no quantum mechanics course I've taken or watched anyone else teach addresses it. Although Wikipedia does. You go to Wikipedia, you see the movie of the particle going, and you can imagine looking and measuring at what time that peak comes out there and comparing it to the time of that incident peak. A little difficult to do by eye, but people starting around 1935 knew how to calculate these things. Basically, it's calculating the group velocity. We learn it whenever we do wave propagation. And there's a problem, which is that the way you usually calculate group velocity is using something known as the method of stationary phase, which, as you can imagine, involves studying the phase of the wave. But it turns out that inside the barrier region, we're not accumulating any phase. We have exponential decay of a wave packet, real exponential decay. The phase is essentially not changing. What that means is that no matter how thick the barrier gets, that phase ends up being a constant. And therefore, anything you calculate from the phase, like this delay time, also becomes independent of that phase, which might not sound too disturbing until you imagine letting d go to infinity, where whatever that finite time is, it will eventually be smaller than d over c. So this seems to violate causality. I think that's why you don't hear about it in courses, because people said, oh, that can't be the right answer. I better not bring up a question I don't know how to answer correctly for my students. You could imagine that the method of stationary phase breaks down. It's an approximation, but it doesn't. All right, it does eventually, but it doesn't need to break down as soon as this occurs. If you look at the simulation, that peak really could be traveling faster than light. You could then argue the Schrodinger equation is non-relativistic. We shouldn't take it seriously. Therefore, people repeated it with fully relativistic equations. The same thing happened. So those are not the excuses. It just turns out that this is true. The peak really does arrive early. That was one of the experiments in my PhD thesis. A number of other groups in the 90s did similar confirmations. Some people had probably understood that long before, but most of us were still confused. But it leaves a more interesting question. Forget about the arrival time of the peak. In some sense, the peak is just a motion of an effect. It's an interference pattern. It's where things happen to interfere constructively, as Büdeker and Landauer, who were some of the pioneers of the more modern approach to this problem, used to say, there is no law about a peak turning into a peak. There is no causal relation between the incident peak and the output peak. So you shouldn't think of that as a thing. It's just a portion of a probability distribution. It therefore begs the question of what the particle was doing while it was getting across. Where is the particle between this incident position and this final one? Just as in the case of my 3-box problem. In particular, can I think of these transmitted particles and these reflected particles as having different histories? Am I learning something new about the particle by seeing which one got transmitted and which one got reflected? As I said, Büdeker and Landauer in the 80s were people who said, you know, we've been circling around this problem since the 1930s and the 1950s, and no one solved it, and they just started ignoring it. But now we have electronic devices that rely on tunneling. And we have systems that we're trying to solve where tunneling is intrinsic to them, and we don't even know what the relevant timescales are. We better think carefully about it. And roughly speaking, they ended up with a bit of an Einsteinian approach, saying we have to think about what we mean by the time. You have to imagine some clock that would measure a time and ask what would that clock be? And they had a number of different approaches to that. The one that, I should just say, not only did they have a number of different approaches and other groups have different approaches, but some of them have been experimentally implemented in the past. This is basically the grandfather of today's superconducting qubits. That's from the lab of Daniel Esteve, who was working with other famous names in this field, John Martinez, Michel de Molay, and so forth in those days, and did this foundations experiment that led Rolf Landauer to say the problem has been resolved. So is that the end of the story? No, as of a few years ago, a bunch of popular science things were even claiming that measuring the tunneling time was a newly solved great mystery of the world, and that it was shown by Igor Lichtenberg's group to be so quick that it could be instantaneous. So back to this question, is it really faster than light? The way we like to approach it is, again, coming back to this weak measurement picture of things. Let's probe the particle while it's tunneling, but do it gently so that we're not disturbing that process. And that idea began with, well, actually began with Bass and Levachenko, but Büdeker is the one who sort of really brought that to the fore, thinking about a very simple clock, which is the fact that a spin processes about a magnetic field. So that forms a natural clock hand. If you have a spin polarized electron tunneling through a rectangular barrier, and then you imagine adding a magnetic field in the barrier along the z direction, the spin will precess in the xy plane at a known frequency. And by measuring the precession angle over here, you would learn what the time was. There are a lot of subtleties with that, but I'm going to skip over them. For the experts, anyone who wants to grab me about them later, please do. We thought the way to do this would be to grab some system with an internal degree of freedom like that spin. Electrons seemed a bit complicated. I mean, it's hard enough to build tunneling devices for electrons, let alone confine a magnetic field just in the tunneling region and have all the propagation be ballistic. Maybe some people know how to do that sort of thing by now. Neutron people, it turns out, do. We did not. We instead thought if you take a Bose condensate of atoms, then that forms a nice coherent, essentially zero temperature source with a long coherence length. And we learned how to cool rubidium down until its coherence length was about 4 microns, which is really exciting because we can make potential barriers out of light for these atoms. And light, as you know, can be focused down to about a micron, hence microscope, et cetera. So we could take a blue detuned 420 nanometer beam that makes a repulsive potential for atoms, focus it to about 1 micron, and cool the rubidium enough that its coherence length is 4 times the size of the barrier, basically what we need in order to study this sort of thing. So we Bose condense the atoms in an attractive potential formed by these 2 red beams shown here. And then we add this barrier whose height is only about 150 nanokelvin, which would sound really small, except the temperature of our atoms is about 1 kelvin. And that 150 nanokelvin in sort of down to earth units for the atoms means about 4 or 5 millimeters a second. If we push these atoms at 5 or 6 millimeters a second, then they all just roll through this laser beam. But if we push them at 3 millimeters a second, they're all reflected. And at 4, some are transmitted, some are. There's just a movie of our atoms sitting on top of a laser beam, slightly different geometry. In the old days, we tried to use gravity to pull them through. So we made a table by focusing down a laser beam. Bose condensed atoms right on top of that, and watch what happens. Now what happens is the hottest ones fall through or over the barrier, and the others just spread out on the table until they spill over the edges. Except all along, there's something tunneling through there. We didn't have the resolution to see it in this image, but there must always be atoms tunneling. We also needed that magnetic field. And the reason we wanted to do this with atoms is because although I don't know how to confine a magnetic field very precisely to a 1 micron region, I know how to focus laser beams down to a 1 micron region. And it turns out you don't need a real magnetic field. You just need anything that couples 2 different states of the earth. So we use these particular states known as the clock states of rubidium. They're known as that because they're so insensitive to background fields that in cesium, they are used as the definition of the second. The transition between the analogous states in cesium defines the second. People can measure it to 15 decimal places or what have you. We're happy to get 2 or 3 decimal places, but it's nice to have that same robustness. And we can couple these 2 states using what's known as a Raman transition, using laser beams. So we can focus beams down inside the barrier and have this effective magnetic coupling occur only while the atoms are inside that region.
So I didn't catch that. How did you get the field to only act inside the barrier?
Sorry, okay. So the nice idea would be, let me take a pair of Raman beams and focus them down even tighter than the barrier. So only when they see those two laser beams is anything going on. In fact, we're not there yet because we already focused our barrier as tightly as we could focus anything. Instead, what we currently do, show up in the words at the bottom, yeah, is we add an extra sideband on the beam that forms the barrier, 6.8 gigahertz away, which is the hyperfine splitting ground state manifold. So there are already two frequency components in the barrier. While the atom is in the barrier, it sees these Raman transitions,
I see.
and as soon as it's out, it doesn't.
Okay, that's fair.
Now, I should be careful. I'm drawing it as a square barrier. So there's a clear forbidden region and allowed region. In reality, we focus a laser beam. We don't get a square barrier. We get a Gaussian barrier. So the time we're measuring is the time spent within that laser beam, weighted by its Gaussian shape. That entire region is not forbidden. Only part of it is forbidden, right, for a given energy. Okay, so we try to account for all that. Those are loopholes right now that we need to work on. So experimentally, we begin with our atoms in this attractive potential, but then we turn off one of those beams. So they're sitting in this sort of one-dimensional waveguide, kind of like a fiber optic cable, but for atoms, which we intersect with this focused sheet of blue-to-tuned light. So we have a nice, simple one-dimensional, quasi-one-dimensional problem where the atoms propagate to the right, where there's also that Raman beam. Some are transmitted, some are reflected. And now in principle, we can measure the rotation of these atoms or the rotation of these atoms and really see how much time each sub-ensemble spent in that region. And this is what the raw data in our earliest iteration looked like. If we turned off the barrier, all the atoms ended up on the right, but then we could do a Stern-Gerlach analysis and really see two clouds, count how many had each spin. When we turn on the barrier, we see some reflected and some transmitted, and we can repeat that analysis. And there's a very, very busy plot summarizing our most recent data. But if you look at the upper curves for now, that's measuring the time that we were originally looking for as a function of incident velocity, but for two different barriers. So the red points indicate a barrier whose critical velocity is given by that red dashed line. And the blue points, the slightly lower barrier, where instead of 4.7 millimeters per second, the barrier was tuned to 4.1 millimeters per second. But what you see is that as I lower the incident velocity, the time goes up. Atoms are slower and slower. It takes longer to traverse a given region. If we had no barrier, we just measured, 1 over v. Very expensive way to do first-year physics. Confirmed that time spent in a region of thickness d was d over v. Classically, that would diverge at the top of the barrier, right? If your energy is just equal to the barrier height, your kinetic energy goes to 0, your velocity goes to 0, and it takes an infinite amount of time to go anywhere. Quantum mechanics abhors infinities. Well, we're discussing that. Maybe it doesn't mind infinities, but it suppresses this kind of infinity in any case. And we end up with a finite time, even when you're at the top of the barrier. Maybe more surprisingly, as I keep lowering the energy further, fire the atoms more and more slowly, this turns over and those red dots begin to go down. It ends up being faster to tunnel through the barrier at lower energies than at higher energies, which makes sense to a New Yorker, at least. I call it the red light effect, because when the red light is on, you're forbidden to cross the street, but if you do, you do it really quickly. So somehow the atoms have the same attitude. And you even see over here that if you go from the 4.7 millimeter a second down, you lower the barrier to 4.1, the atoms start taking longer to go across that lower. So that's one of the things that we observed here. And again, there are a lot of details that I left out, but that's because I just want to give you the big picture for now of a few different projects. Happy to follow up with others. The big future goals we have on these experiments are to ask not just how much time the atom spent, that's just a number. I'm not that interested in numbers, but where it spent it. What is the history? What is the trajectory? And for this, I would just need to focus those beams down more tightly, which we can't do yet. So I can have a probe that's looking, let's say, only at the left-hand part of the barrier, or only at the second fifth or the third or the fourth. And that way I could measure how much time either the transmitted or the reflected particles spent in each region. These are the predictions for that. If you post-select on reflected atoms, shown in red here, it turns out this is very simple because almost all the atoms are reflected. So post-selecting on reflected atoms and not post-selecting at all is basically the same thing. I'm just asking, where's the probability density? What is psi squared? And we already know that decays exponentially. So there's my exponential decay between the left-hand side and the right-hand side of this 2 micron wide barrier. Interestingly, this goes back to the origins of weak values and time symmetry of quantum mechanics. If you look at transmitted particles, you end up with an expression, other than a complex conjugate, is completely time reversal symmetric. I know the particles came in here, but I know they came out here. Both of those pieces of information are equally informative and powerful. And it means I have to get a symmetric function popping out at the end. And I get this green curve. But the interesting thing is it's built up of all the same functions that were in the original wave function, decaying and the rising exponentials. So there's a part that decays exponentially here and a part that grows exponentially here. Beautiful symmetry that you don't have for the reflected portion. But you still get exponential suppression at the center. So we began with this mystery of how do particles get across a region without seeming to spend enough time there. And we come around to the same mystery because it still seems as though the particles don't need to spend any time in most of the barrier. They spend some time entering it and they spend some time leaving it, but you never find them in the middle. And I'd love to see that experimentally. And I'd also love to think more about what that means and how to get my head around it. Yeah.
So first question, why was it important for you to have a coherence length that was longer than your barrier?
Okay, so that's a very rough way of putting a requirement to get into the tunneling regime. What I would really say a little more carefully is that we want our energy to be below the barrier. We want it to not necessarily be too far below the barrier because we need to have some significant transmission probability. But there'll always be some range of energies. And if the range is too big, then there'll still be some above barrier components and we'll end up contaminated by those.
I see. So your coherence is more just to get a sort of uniformity in your distribution of particles.
That's right. We want a nearly monochromatic beam of atoms.
Okay. Now, wouldn't this measurement, I mean, knowing where the particle is within your barrier is obviously going to affect your coherence length.
If we really knew where it was. So again, these, and I didn't say it, you're right, these are predictions for the weak measurement. So the case where I measure on average how much of their time do the transmitted particles spend at this point, but without ever doing such a clean measurement that I know for sure one individual particle was there. But I'm going to come back to that.
I see. So I see. Okay. I see where you're going.
And so on average, yeah. And I probably have words about this for those of you, probably all of you, who know about real and imaginary parts of values. I'm only telling you about the real part here. And the opposite is true for the imaginary part. The imaginary part is pretty big all the way across. So there is a sense in which the particle maybe spent some time or did something, left a trace, as Lev would say, in the middle of the back. We also want to compare the transmission and reflection, as I was just doing. Why didn't I show you those results for the first experiment? It's because they didn't make sense to us. And as always, we keep quiet about results we don't understand. But now we understand them. They're about to come out in PRL. When we looked at our clouds and measured SX, SY, and SZ to do the full tomography of the spin, we found that we didn't just get a number. It depended where in the wave packet we looked. We saw these spin textures where the spin even had one sign at one part of the wave packet and a different sign at another part. And each color here is for a different strength of that affected magnetic field. Even the sign of the effect could change as we change that magnetic field. That made no sense to us at first. It's never what happened in transmission. And we realized that our atoms collide all the time. There are interactions between rubidium atoms at the densities of the BEC. We went out of our way to lower the density until we could neglect those. That always worked. And we didn't take it for granted. We verified. My students would do the non-interacting simulation, the interacting simulation. They both agree. We'd say, okay. But we hadn't looked at reflection before. And eventually we realized it's one thing to have a wave packet all propagate in one direction through some region. As soon as you reflect one particle, it's got to fight its way back through the rest of the cloud. It has many more opportunities to collide. And interactions became absolutely essential for understanding the reflected wave. So these are simulations done with the Gross-Pitaevsky equation, in other words, the non-linear Schrodinger equation, the one that takes interactions into account. And you see beautiful qualitative agreement with the experiment. The Schrodinger equation doesn't do that. You just get smooth wave packets with a constant spin. The dirty secret is that people in ultra cold atom physics know that rubidium is a beautiful atom in part because this weird coincidence means that rubidium scattering is spin independent. It doesn't care about the spin of different particles. But if that were true, why would interactions lead to these spin textures? And that took us about a year to address. So rather, David came up with a really good explanation for it right away. So we invited one of the world's experts in the field to sit on his thesis committee. And the guy came in and explained that it was impossible, that everyone knows that it doesn't work that way. So we spent another year and picked up Joseph Tywissen as a collaborator to really show that the whole community had, I think, been missing something about the importance of exchange effects, the indistinguishability of these particles when you have collisions. The simple story is the following. If I have a wave packet coming in and then I reflect some of the particles, I build up a standing wave. And in a standing wave, there are regions of excess density, or position-position correlations among the particles. And that gives me a stronger interaction energy than I'd get if there were no interference pattern. Well, if the particles aren't indistinguishable, for instance, if I flip one of the spins, then there's no interference pattern. So it turns out that the non-spin flipped state sees a different interaction energy from the spin flipped state, even though the interaction Hamiltonian is spin independent. And this is something that was well known for a long time, that people associated it with bunching and thermal states and would repeatedly write that this can't happen in a condensate. And that's where it turns out they were wrong. Once the condensate includes multiple modes, this indistinguishability effect happens even in condensates. And the final goal is what John was alluding to, I think, earlier, which is what happens if I find a particle in the barrier? Doesn't that modify its behavior? And I've been thinking about this for a long time. Yeah, apparently for 25 years. Since I gave a talk about this stuff and sort of offhandedly said, obviously you need to measure this weekly so as not to disturb the particle. And Bill Phillips was in the audience. And those of you who know Bill understand that he immediately interrupted me to say, well, why not just measure it strongly? What will happen? And I explained the following. If you measure strongly the particle is in the barrier, for instance, you shine light on it, and when the light scatters off the atom, you see it on a screen and you say, look, I learned the particle was over there. Well, if you do that, you've in some sense collapsed the particle to be here. If you collapse a particle to be in a given region, it has enough energy to be in that region. There's no way around that. So it's no longer tunneling. Now it'll just roll over that barrier one way or another. And of course, Bill knew that. He said, yeah, no, I understand, but how does that happen? Where does it get the energy? And I wrote this mostly incorrect paper trying to answer that question. Now I think we have it right. Because we thought of a way of doing it. And what we were thinking at first is there a way, instead of doing these weak spin measurements, I could plop a really whopping magnetic field down at the beginning of the barrier, flip the spin 180 degrees, and say that was a strong measurement. Flip the spin 180 degrees, so I really know it was there. And the problem was experimentally, we didn't know how to do that because we don't even know how long it's spending there. How do you do a pi pulse if you don't really know the interaction time? But after a few years, we came back to this and said, we don't need to do that. Stick to the weak field that we had before that rotates you by 5 or 10 degrees. If you then look at the particle in the original basis, you'll either see it in its original spin, plus x, we call it, or sometimes you'll see it along minus x. But if you see it along minus x, that means it's not along plus x anymore, right? Something happened to it. And the only thing that could have happened to it is that magnetic field. You'd never find minus x if it had not experienced that field. So every time you see that, you've learned that particle saw a magnetic field. You said, well, that's a probabilistic, but a good way of guaranteeing that the particle was in that magnetic field region. And my prediction was, if I collapse it to be in this region, I've then given it enough energy to be there, and it's now free to roll over the barrier. First of all, we'd love to see that because it means you could take an arbitrarily thick barrier and enhance the transmission probability by the mere act of looking at it. If you look at it well enough, then you can cause particles to get transmitted. I need to see that a lot, right? So we said, let's look at the ratio, the transmission and the reflection probabilities, after post-selecting on those spin-flipped atoms. Blah, 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 blah.
That sounds like Andrew's measurement motor.
It's all related to these sorts of things, yes. And also to Caldera-Leggett and much older stuff in condensed matter physics. I probably should have separated out these plots. The blue curve is what David calculated when I asked him to run these simulations. And this is on a semi-log plot as a function of where in the barrier I put that probe. And I'm measuring again the ratio of transmission to reflection. So 10 to the 0, or 1, means 50-50. That's what we wanted to find. And instead, I found this nearly straight line, which means an exponential dependence on where you collapse the particle. If you collapse it in the middle, then transmission and reflection become equally likely. But if you find it on the left, it'll probably leak out to the left. And if you find it on the right, it'll probably leak out to the right. And the ratio is e to the 4 kappa x, which basically just means it looks like tunneling. It was exponentially less likely to get to the further edge of the barrier. But this is really weird because it's saying this particle is acting like it's below the barrier. It has this exponential dependence on distance, but like it knows where it began within the barrier. And that's exactly what we thought was impossible. You can't know that you're in the barrier and know that your energy is less than the barrier energy. But that's kind of what that behavior looks like. So already that would be fun to verify. It wasn't what I wanted, and that should have been obvious because we imagined a time-independent magnetic field coupling these states. And we know that time-independent fields don't change the energy. I was saying we expected the energy to change. So it couldn't possibly have happened. We needed to have this probe be time-dependent, pulse on the probe, and then see whether or not some of these spin flipped. And the intuitive argument behind that is that this time-independent probe is not teaching me the particle is in the barrier now. It was just teaching me, yeah, that particle was in the barrier at some point in history. That's not enough to collapse it. To collapse it, I need to know there's some point in time at which it's in the barrier. And indeed, when David made the probe short enough, he eventually saw this 50-50 transmission reflection. So that's one of the things we're trying to figure out how to do in the lab in the future. But the question it raises is, what makes it fast enough? What is the time scale? Because that's basically saying, if I saw that the particle was in the barrier now to within plus or minus some delta t, is that enough to conclude that there was some point in time at which I really know it was in the barrier? It's asking, how long should I think of it taking for a particle to leak out of the barrier if it was in the barrier at some point? So yet another time scale for tunneling. And we thought we'd go through and look at this and probably just rediscover one of the longstanding contenders for tunneling times, but we did not. And the result that we find depends on the position, depends on where you are. And I said, oh, that's okay. We'll discover a velocity scale that must already be known. And we'll see that the time scales, linearly with distance to the edge of the barrier. It doesn't. It scales as the square root of the distance to the edge of the barrier. We have numerics and also some approximate analytics to support that. Zero intuitive understanding of why that should be. What does it mean for something to be proportional to the square root of a distance? I mean, it's what happens under Newtonian gravity. It's things accelerating out, but there's no reason to think of that as the appropriate description for this problem. So don't know what to do with that, but there it is. All right, so I've now used up something like 3/4 of my time and one third of my topics as expected. So we'll just go as the square root of distance.
Could it be that it's accelerating the particle once it gets to, you can imagine, this barrier is actually, you could imagine that it's
yes and no. That calculation is for a square barrier, so there isn't even a force, right? Except right at the edge. So I don't see a natural way to describe it as an acceleration. But you're right. We're talking about something in a repulsive region. Maybe there is a way to close that circle, but I haven't found it.
I think there is.
Okay.
Play that way.
I was going to come back to these pilot wave simulations. Good.
Yeah.
Well, honestly, photon trajectories, as we've discussed before, are certainly another way that some theorists back in the 80s, 90s more thought about treating tunneling times. And we've done some experiments measuring photon trajectories for photons. I would love to actually measure the bone trajectories for the tunneling atoms. That's much harder. That's going to be my retirement project. My students' retirement project. But we'll get to it. Anyway, so the next project I want to tell you about, and again, if I lost you earlier, or you're just tired, wake up now, it's a completely different topic. Was originally this, we're trying to make photon-photon switches. This is what we think of as our applied side, make a logic gate for a quantum computer. But unfortunately, we ran into a foundational question and we're easily distracted. So we gave up on the applied side and we're now thinking about the foundations. And as I said, the question is really, how does light slow down when it goes through matter? And this is one picture we often get, that photons get absorbed temporarily and then they get re-emitted. And it means there was some time wasted while they were stuck as material excitation. And that's not crazy. This is something that people used to tell me with a few caveats when I was a student, that even in a piece of glass where the photons are nowhere near the resonances of the material, you can interpret the Heisenberg energy time uncertainty principle as saying you can kind of violate energy conservation for a little time, as long as the time is less than h bar over the energy difference. And that would say, even when you're really, really far away from that ultraviolet resonance in the glass, the photons get to spend a little bit of time stored as atomic excitations. And it sounds dangerous, and real field theorists hate this way of talking, and they don't believe in energy conservation violation. But if you actually draw the index of refraction for a normal Lorentz medium, far from resonance, it goes as 1 over the detuning. It really is 1 over this energy deficit. So again, it's not crazy. You'd imagine this probably doesn't work closer to resonance because, well, 1 over the energy deficit goes to infinity. We don't think it's going to take an infinite amount of time. But also, we know that there's a lifetime to these excited states. So I might have thought that this time would saturate and atoms would never spend more than their natural lifetime in the excited state or something like that. But it's even worse than this suggests, because that's just the index of refraction. That doesn't, in fact, describe the delay time. The delay time is given by the group velocity, which has some extra derivatives in it. And although it looks like 1 over the detuning far from resonance, it goes completely haywire and goes to a huge negative number on resonance. The velocity, group velocity, is actually negative on resonance. So the peak of a pulse comes out before the pulse comes in, reminiscent of this tunneling stuff. So really don't expect this picture to work at all. We were able to put something together a little more rigorous. I'll skip all the mathematical steps, but we switched to really thinking about light going through a cloud of atoms exactly on resonance, and asked, what's the probability of a given atom being in the excited state? Well, anyone who does any atomic physics or atom light interactions knows how to do that. It's related to the intensity and the units of the saturation intensity. We know what the saturation intensity is, and most of the constants cancel out. And you end up with a remarkably simple result, which is that if you just integrate the time all the atoms in the cloud spend in the excited state, the answer you get is equal to the spontaneous lifetime of those atoms multiplied by the number of photons that got scattered, the probability that your photon got scattered, which has a really easy interpretation. It sounds like some fraction of photons got absorbed. When they got absorbed, they excited an atom. The atom was stuck in the excited state for, on average, a lifetime, and then it decayed and the photon got lost through spontaneous emission. The other photons were the ones that just got lucky, didn't get absorbed, made it all the way through the medium. And this is what intrigued us, because we were trying to look at the effects of these photons and interested in post-selection. And my student, Josiah Sinclair, came to me one day saying, well, wait a second, if we know that the photon got through, doesn't that mean it never excited the atoms and it won't have any effect at all? And that's what we set out to demonstrate by looking at what's known as a current nonlinearity. The idea being that as these photons go through, if they excite atoms into the excited state, they lower the number of atoms available to create an index of refraction for anything else. So if I send a second beam through the atoms and I'm measuring its phase, I'm measuring the index of refraction, I'll see a change due to that first photon going through. And we see this all the time, but our question was, would we only see that when the photon gets absorbed and see 0 when the photon gets transmitted? Some people gave us the opposite argument. And they said, no, you're wrong to think that way. Every photon is just an electric field. Electric fields couple the excited and ground state. They're all coupling the excited and the ground state. But on the other hand, the scattered photons mostly got scattered within the first absorption, length of this medium. But if a photon came out here, it must have got through the entire medium. So it could have excited all the atoms. So in fact, it'll give you an even bigger phase shift. So this is what Josiah and Daniela and Kyle decided to verify, sending in effectively a pump photon here, looking at the phase shift on some other probe beam, but then trying to detect the pump photon at the bottom and say, let's just look at the phase shift when I see a photon there and see what happens. That's what it looks like experimentally. And these are some of our experimental data. And the only thing I want you to take away is that these regions over here are not equal to zero. We really expected zero. It took Josiah and his buddies really something like 600 sleepless hours. I think in something like 800 hours of real time, they took 600 hours of data that involved someone always there running the experiment and just barely showed by a few standard deviations that there was something there. It took us another year with Howard Wiseman's help to come up with a quantum theory to say what the answer should have been, because this cannot be treated semi-classically. We can make up nice semi-classical stories, but you can't talk about post-selecting on where one photon goes in a semi-classical theory. And quantum theories of post-selected open systems are rather complicated. Howard saw the right trick to simplify it. I skipped a bunch of the other slides. He came up with a really complicated integral formula that my students then calculated numerically, and they gave me a plot that went negative. And I said, just come back when you fix your numerical error. And one of them was smart enough to show me that you could analytically take the limit of Howard's equation, and it does go negative. So I yelled at Howard, and I said, come back when you fix your theoretical error. Howard doesn't make mistakes either. So it actually goes negative. And what Daniela, Kyle, and Vida have recently demonstrated is that we really see that in the lab. By changing the bandwidth of the pulse with the RMS duration and playing with different ODs, we see this measured time go from a positive number to a negative number. Turns out that negative number is exactly the group delay. I told you before that on resonance, the group velocity is negative. So the funny surprise is that simple-minded picture that I said should break down on resonance, which is that the extra time something slows down in matter, is just the time spent in the excited state. It works even when the extra time is negative. If what you mean by how much time is spent in the excited state is what you get by measuring it weekly. Obviously, there's no way I can, strongly measure the probability of something being in the excited state and get a negative number. I always mean this in the context of measurements. But it turns out that that is the right prediction. So that was part 2, and it has other things. And part 3, I'll just show you the pretty pictures. As I said, we want to think about what it would mean for a quantum brain to make observations. My postdoc, Aaron Brodich, had the beautiful title, Do Qubits Dream of Entangled Sheep? And the question is just, when I measure a system, I observe the system and I get some classical information out. But if I were a truly quantum observer, then my memory could be a quantum mechanical storage device. And instead of putting a classical number in my memory, I could put any quantum state I liked in the memory. Now, as a classical observer, if I measure position, we all know I can't measure momentum. In fact, I destroy the momentum information. And if I measure momentum, I can't measure position. But if I were a quantum device, I could just store the whole wave function in my memory. And in some sense, I would know everything. I know the whole wave function, x and p, that I can make some inferences about later. Got to be some trade-off, obviously. And the trade-off is that if I measure both x and p, I disturb both p and x. And that's known as the no-cloning theorem. If I put your wave function in my memory, then I have to erase your copy of the wave function. What I can do is something like a swap operation. You might think that's not an interesting way to do an observation. In some theoretical sense, that means doing the complete measurement of the system. And you could also imagine doing something swap-like, but more weakly. And this is where Aaron, along with my students Noah, came up with the observation that the disturbance of a measurement can be erased. Most of you know about the quantum eraser. but it can only be erased probabilistically. You make some other measurement, and either you get the erased copy, or you get some somewhat distorted copy that you could fix later. But you need to store this one extra bit of information. Now, what they realized is that for these quantum sorts of measurements, like a swap or even a partial swap, you can still erase that disturbance, but you need 2 bits of information to do it. You need a 2-bit channel in order to erase this. And it's not because the measurement is strong. It could be a very weak measurement. It's fundamentally because of the type of interaction Hamiltonian between the observer and the system. So we've done one experiment following up that theoretical work, and this is on the archive now from Arthur, looking at how with a von Neumann style measurement or this swap-like measurement, as we change the interaction strength, we get more and more information. That was sort of well known from the beginning. But also how if we only use 1 bit to do the erasure, we never get up to the full original information. And if we use a 2-bit erasure channel, we can. That's in contrast to the sort of classical like von Neumann measurement, where 1-bit erasure is shown in these red points, and it gives you all of the information. So I think there are just deep questions about what it means for one quantum system to observe another quantum system, and what kind of disturbance you end up with. And the kinds of directions that we're thinking of going there are related to a lot of these Wigner's friends controversies that many of you have probably heard about. And in particular, there's an idea of doing an experiment where we have one system, but 2 different observers trying to study the system. And if they were just measuring something classically, if they measured the same thing, it would always be consistent. If they measured conjugate observables, they would disturb each other's observations. But what happens if they're both trying to measure everything at the same time, 2 different swaps going on at the same time? And I think, this is just the first doors to a series of really interesting questions, and also connected to things that people in both many body physics and quantum information are concerned about, of different couplings and things like spin chains, because the distinctions I'm talking about are basically related to the difference between Ising-like and Heisenberg interactions. It just turns out there are really fundamental differences between these different sorts of interactions. So that's just the beginning. There's a list of many other things that we're interested in, metrology and closed time-like curves, and how to make Fabry-Perot cavities for atoms. And here are a few more papers that have recently been published or in press now on some of those topics. And as always, I'd be really happy to tell anyone about any of those, but I'll just stop there. Thank you very much for your attention.
Questions? Vivek.
So I was thinking of combining your part 1 and part 2. So in your part 1, if you put Pluton's barrier and you ask how much time an atom spends in the middle, wouldn't you get a similar figure? You'll have, if you have classical, then it can spend infinite amount of time, but quantum mechanical, you finite lifetime.
I'm not sure why classically it would spend an infinite amount of time, but we're certainly interested in this double barrier idea, or the Fabry-Perot, basically. And it is very similar to what happens in tunneling. It turns out a lot of these pictures share one feature, which is that when the transmission is very unlikely, when you're right at the absorption line, or when you're well under the barrier, you get very, very short times. And when the transmission is very likely, like on resonance for a Fabry-Perot, you get incredibly long times. So yeah, the weak value of the time spent inside that cavity, inside that double barrier, looks qualitatively like the transmission curves. It has this peak on resonance that basically goes to the ring down time, and then it goes smaller than d/c if you're right between the 2 resonances. We haven't yet tried to measure that, but we are building a Fabry-Perot cavity for the atoms now. So that is an interesting topic for the future.
I think if you just look into the semi-classical picture, then you have a resonance, right? That's it. You get the peak around the resonance, and then you go flat, right? But then when you add the second order effects like quantum mechanical, like virtual states, then you get some the plot like you have for the group delay, where you have like renormalization of resonance as well. You will get,
I'm not sure what you mean by a resonance semi-classically. I mean, if I just had sort of one big square barrier, then I certainly get this divergence and something that comes down smoothly. And quantum mechanically, right, I get ripples around that smooth
Yes.
curve.
You don't get the divergence anymore, you denormalize.
That's right. So yeah, we're gonna look for those resonances. In a Gaussian barrier, it turns out you don't get any above barrier resonances. And we're collaborating with Micheline Soli on this. It turns out that's believed to be related to these questions of PT inversion symmetry and reflectionless potentials. So their assertion is that if the top of the potential is quadratic, then there are no points that are strictly reflectionless. And that's the situation we have with the Gaussian. But if it has a higher exponent, x to the fourth, x to the sixth, x to the eighth, then you start getting points where it's strictly reflectionless. And of course, the square barrier is kind of the limit of that, where you get lots of points of resonant transmission. So we've set up a spatial light modulator so that we hope we can make barriers that we tune the shape of with sufficient precision to see that, but we'll see whether that works or not.
I think Matt was next.
Yeah, so the 2-bit erasure for is extra quantum measurements. Is that related to teleportation of superdense code?
Yeah, that is how you erase a swap. Because you just teleport it back where it came from, and that requires 2 bits exactly. But mathematically, they were able to show a general result about the necessary channel capacity and the rank of the operator in the interaction Hamiltonian. For a single qubit, the only options are 1 or 2, but it's in the general result.
Jeff.
I have a kind of a prediction. I wonder if you saw in the a couple slides ago, the one that you do with Howard on the open quantum system. As the crazy delay time becomes more negative, do you see? I predict that you could actually increase the strength interaction beyond the normal regime of weak measurement, and still effectively it would be a fully. You would see all the results you would normally see in a fully weak.
All right, we should talk more about that. That would really surprise me for the negative one. I feel like that shouldn't be the, but I know the cases you're alluding to.
Okay.
Experimentally, we can't do that here. We're fundamentally 10 digits into the weak regime, even if we didn't want to be.
Okay.
But we can think about other experiments where maybe that would change.
I predict that it could be. It's a kind of a new way of making a truly weak measurement, but in a much stronger. In what should be a strong measurement regime.
I mean, we did come up with some nice pictures, and some of them I think are already in the press, showing how this is analogous to some simple interferometers where we know that we have negative weak values. And you're right, in some of those cases, we know the strong value is also negative.
But the more crazy the negative delay gets, that would I predict that would actually allow you to make a stronger outside of the
in
normal
some
realm.
sense. In dimensionless units, this negative delay is just -1. It looks like a weak value of probability for being in a certain path of an interferometer going to -1, sort of like in the 3-box problem.
It saturates it.
Well, so as a time, it goes to minus the optical depth times the lifetime, which happens to be exactly the group delay on resonance. But it never goes further than that. That's as negative as it gets.
Interesting.
And that's why I say in natural units, it's really just -1. But we should talk more, because I like the idea of looking in the strong regime, but as I say, probably in a different experimental system.
Yeah.
Other questions? Yes, Tafari.
Yeah, so in the first part, you showed that with when the velocities of these atoms are getting smaller, you're saying smaller and smaller tunneling times. So do you know the dependence of the tunneling time in those cases?
If I know you mean, could I tell you the formula right now? Then no, but if I know you mean, is that formula known and could we write it down for you? Yes, it's in the papers. And yeah, no, it really. In fact, there's a sense in which I can tell you. The group velocity is just the derivative of the transmission phase with respect to incident frequency. It turns out these other times are the derivative of transmission phase with respect to the barrier height. If you're in the regime where all that matters is the difference between the two, those are actually exactly identical, but there are other regimes where they're different. So yeah, we know exactly how to come. We knew that it should come back down, but it had never been observed experimentally.
Okay, any last questions? If not, let's thank Ephraim again.